Michael, and good morning. So I will guide you through the notes in this video, and you should look at the uh, dates at the top of the notes. So there we have the original dates. So it's supposed to be on the 12th, but I finished these notes on the 15th. Yes, it's a bit late, but I think you can, given the basic that we've covered from the polynomial section. So the introduction to the Newton-Cotes integration would be not as difficult as you would have imagined. So let's have a look at the Newton-Cotes integration. So this integration is a numerical integration based on the Newton's polynomial, and the formula, the generalized formulation gives you the Simpson's 1/3 and 1/8 quadrature rule. And I will use the term quadrature and integration a lot here, but when I say quadrature, it simply means numerical integration. Now let's go to the basic idea. So if you have a function that you want to integrate, this function can be a continuous function. Some things that you some function, the function may be something that a known function, or it can be a function that you created from your experimental data. It doesn't matter, but as long as you want to turn it into a numerical integration, so you will have the continuous version and then you will have the approximate one. So the idea here is to use the Newton's polynomial to approximate the continuous function, and the form of the polynomial is simply, if you look at the first two terms, it will be a linear equation, and if you take it further down to the third terms, it will be a quadratic equation, and so on. So the integration in this case become I equals integral from b to a for the fn, which is the discrete function or the constructed polynomial function, and all you have to do is just replace the definition. Now in the case of linear approximation, so here you have, let's say you have your continuous function and your approximate function is in the form of a linear equation. So the first thing that you need to do is to derive or to solve the value for a0 and a1. Now if you have two unknowns, then you will need two equations to solve them. So in this case you have you will need the value of f at a, okay, which is f at xa actually, and also f at xb, okay. And when you have these two equations, you can solve them for a0 and a1, which will give you the common linear equations. You can either write them in this form or in the form of the more comfortable one, like this: y equal mx plus c. Either form will do. Now next is to just plug the equations into the approximate function into the integral, and you go through all the integrations as it is. So here you have fa, for example, and then when you integrate them, you'll treat the fa as a constant. So you have the x here, and of course you have x minus xa, so this will be x minus xa squared divided by 2. So this is a very rudimentary integration process. So once you solve the whole equations with some little algebraic manipulation, you'll get the final solutions. And if you observe this solution, it is actually the area for a trapezium, and that's why this rule is called trapezoidal rule, because it's basically approximate the function to the form of a trapezium. Now in practice, for programming purpose, you don't just do what do you call it? You don't just integrate from point A to B. What you do is you divided the domain from A to B into a smaller section, and with each domain, the width of the divided section will be h. Usually, for practical purpose, it will be an equidistant h, so you don't have to complicate your program. And then in each section you have the numbering, so depending on what kind of programming language that you'll be using, you can start with either n equals 0 or n equal 1. Fortran is 1, and I think MATLAB can, if you're familiar with MATLAB can start from 1 and 0 too. MATLAB can start from 1 or 0. Python is the same. Python can start from 0 or from 1. Okay, but C, if you want to use C starts from 0. So the indexing depends on the programming language. So for this discussion, I'm going to stick to the Python format or the MATLAB format. So n, the index will start from 0 until n. So you have the equidistance of the size b minus a divided by n. So if you go through the whole domain of the integration, section by section, you can have section 1 excuse me, you can have section 1 to be 1/2 fa plus h multiplied by h. So these two are the size of a smaller trapezium. And as with the pseudocodes, now I am not writing this pseudocode to match the explanation here. What I did was just pick up an old code that I have. So as you can see, I'm basing it in the odd index instead of the even index in n, but nevertheless the explanation is the same. Okay, in the end, all you have to do is sum up every section of the trapezium. So your first assignment for this chapter is to write the code in Python to solve a value of the integral fx dx using trapezoidal rule, and the function will be x squared plus 2. Now my suggestion is for you to use ChatGPT. So I'm going to write it here. You may use ChatGPT to write you the code, but you need to check for the solution. You need to check for the solution to be analytically correct or not. Okay, so that's the first assignment. What I want you to do is to write the code and put comments on the code. Explain what the variables are there for, and that'll be the first assignment. Next, we look at the use of quadratic approximation. Now, the first one is the linear equation. So you have here a linear equation, and next up is the quadratic equation, and this is where you get the Simpson's one-third rule. So the idea is just an extension from the linear equation, where you just extend the Newton's polynomial from linear to a quadratic equation, and because of that, you're going to need at least 3 data points for the function for the integral. So in this figure, in the sketch, if you look at the axis, so you have x0, x1, x2, and also f0, f1, and f2 to match the data points. So in this case, we will limit the discussion to the equidistant space. So we have equally spaced size of the data. So you have h equal x1 minus x0, x2 minus x1. Okay, and we will be using, just for this course, of course you may use a backward or even centered, doesn't matter, but just for the sake of our discussion, we're going to keep a consistent approach, so we're going to use the forward difference. So because of that, our next approximation of the function will be anchored on a0 on the starting nodes. So we will have f and x equals a0 plus a1, which is a1, so x minus x0, so this is the anchor, x0, and you also have a2, next coefficient, and the multiplier will be x minus x0 and x minus x1. So we are moving forward in the data nodes. Now clearly, if you just replace fx with x0, you will have f0 as the anchor, so a0 will be f0, and then all you have to do is find the value for a1 and a2 to construct the function. So now that we have just two unknowns, and we can create two equations from the data, so what we end up with is a1 equals the f1 minus f0 divided by h, and while a2, we can directly apply the divided difference equation. Now there are many ways to get the value of a2, but in this case I'm using the divided difference technique because this is the more common approach in solving the coefficient for Newton's polynomial. So we end up with fn x equals to f0 plus a1, which is, this time we have the value f1 minus f0 divided by h, and then plus a2 multiplied by the terms here, x minus x0, x minus x1, and this time we have the f2 minus 2f1 plus f0 divided by 2h squared. Now for the first step is we need to integrate from the starting point, the starting nodes x0 until the end nodes, which is the x2. Okay, so our first section for the integration will involve this area. So if you do the integration one by one, terms by terms, and you finally end up with h divided by 3 multiply f0 plus f1 plus f2, and if you look at the coefficient here divided by 3, so it's the multiplier is 1/3, hence the name 1/3 rule. Okay, now this formula, this conclusion is valid for only the first 3 points, but if you want to extend the integration from, let's say, from 0 to n, so the whole integration becomes something like this. Okay, where f0 is the starting point, fxa, and fn is the endpoint, fxb. So the second assignment will be for you to show that these terms came up when you integrate for the whole domain. So prove it. Okay, so this will be a handwritten assignment. So that's it for our Newton-Cotes integration. I'm not going to go into the 1/8. So let's see, we have here 1/8 rule. So I'm not going to discuss this 1/8 rule because 1/8 rule is just an extension. So we have the linear Newton's polynomial, and then we have the quadratic form, and then we have the cube form. So 1/8 rule is just the cube form of the Newton's polynomial. So I'm not going to discuss that. It's up to you to try it out yourself. But I think you can, from the first one step, from the first trapezoidal rule and 1/3 rule, I think you can come into the conclusion yourself. Now, next up in the numerical integration, we have the Gaussian quadrature. Now, Gaussian quadrature is very unique and a very powerful numerical method, because instead of using analytical solution where you have to analyze the integration by hand, you can actually solve it numerically and still it is the same. You will get to the exact solution of the integral. So this is the main feature of Gaussian quadrature. The only problem is that you have to this type of integration, this type of quadrature can only works on known functions. Okay, you can integrate most of known functions, but there are known functions where you cannot just analytically integrate it. You have to integrate it numerically. So this is the time. This is the case where Gaussian quadrature becomes very powerful and unique at the same time. So let's have a look at the concept for the Gaussian quadrature. So given that you have an integration, now notice the range here. It's not from A to B. It's not from arbitrary space. It's from -1 to 1. And if you want to extend it to any arbitrary space, it'll be I'm going to explain that later. Okay, never mind. So it starts from here. So the integration domain is from -1 to 1 of any function fx, and you can write the integral into a numerical form of wi f summation of wi, the weight, this coefficient is called the weight, multiplied by fxi. So again, fxi must be a known value, so the Gaussian quadrature is not suitable for integrating tabulated data. Of course, there are a workaround to that, but it's not part of our syllabus. Now, because we are free to choose how many points we want, in this course, the discussion we will limit our discussion to 2 points, and of course 3 points, which will be your assignment. So 3 points. So we will only limit our discussion. We will limit our discussion to 2 point quadrature and 3 point quadrature, because most of the time that is good enough size of integral. So let's say you have let's say you want to use 2 point to integrate. So let's look at the step. So the simplest form is Gaussian quadrature, 2 points. So if you write the summation into its component, so you have integral I equals integration from -1 to 1 fx dx, which is equals to w1 multiplied by fx1 plus w2 fx2. So here we have 1, 2, 3, and 4 unknowns. So we need 4 equations because we have 4 unknowns. The unknowns are w1 x1 and w2 x2. So the value of x1 and x2, the value are unique. You cannot just use any arbitrary points or arbitrary x values. It must be within -1 to 1, and it's unique. So the idea of Gaussian quadrature is that you have to use this basis function. Okay, now that you have 4 unknowns, so you need 4 basis functions to create 4 equations. Okay, 4 unknowns, 4 equations to solve. So let's start with the first basis, which is 1. So if you integrate from -1 of 1, so you'll have a function. In this case, the function becomes 1. So you have the weight 1, w1 plus w2 equals 2. So this is the result of integration -1 to 1 for 1. So that's your first equation. The next one is to use the basis x and integrate it from -1 to 1, and you have 0. So for this case, the function is the function fx is x, so the value will be w1 multiply x1 plus w2 multiply x2 and equals to 0. So this is your second equations. The third equation, again, you integrate for x squared. So this is the third equation, integration from -1 1 x squared dx, and you have the solution to be 2/3. So it's w1 x1 squared plus w2 x2 squared equals 2/3. So that's our third equation, and our final equation will be integration of the basis function x cubed x power 3 from -1 to 1. So you have x power 4 divided by 4, -1 and 1. So you have the equation is w1 x1 power 3 plus w2 x2 power 3 equals to 0. So that is your fourth equation. Now if you look at them, arrange them carefully, so you have equation 1, equation 2, equation 3 and 4. Now because of the integration domain symmetry properties, so you basically integrate in a symmetrical domain from -1 to 1, you can add a further simplification for x1 and x2. You can make the x value to be symmetrical. So in this case, you can enforce the condition of x2 equal minus x1, which simply means that you have from here -1 and 1. So this domain at x is symmetrical, so 0 at the center. So you can make x1 somewhere here to be equals to minus x1, which is the x2. So if you put that condition, what will happen is you will have the equation number 2 to be w1 x1 minus w2 x1. And since x1 cannot equal to 0, okay, we don't want the value of x1 to be 0, because that would leave us with just 1 point. So you have the condition of w1 minus w2 equals 0. And here you have w1 plus w2 equals 2 from equation 1. And you have another condition of w1 minus w2. Excuse me. Excuse me. So there you have w1 plus w2 equals 2 and w1 minus w2 equals 0. And the solution is w1 equals w2 equals to 1. So this is the weight that we're looking for. The next one is, of course, to find the value of x1. Now, since we put the condition here, symmetrical condition, since we put this symmetrical condition here, now we can simplify equation 3, where we have x1 squared plus w2 x2 squared. We can make them both the same, both of the same here. And again, with some algebra, w1 is already equals to w2. So you have 2x1 squared, and you end up with the final solution of x1 equals 1 over square root 3. And when we solve for x1, we also solve for x2. So in the end, the weight for w1 and w2 are w1 equals w2 equals to 1. So these are the weights. And the abscissa, or the root, actually, the simple terms is just the root. The root for the the integral will be x1 1 over square root 3, and x2 minus 1 over square root 3. So the next assignment, your final assignment for this session, is to derive the value for 3 points quadrature, and the condition are given here. Okay, so the graphical explanation for this type of integral will be, okay, So you have 0, minus 1, and 1, x, and the power 3, so this is the part, the cube, okay, should be a curve of something like this. So you have 3 roots or abscissae to find. So this will be your x2, which is equals to 0. This is your x3. This is your so okay, let's see, 1, 2. So this is x1, this is x3. So this will be your final assignment. So let's see, we have 3 assignments. You can submit assignment 1 and 2 together because that's just a written assignment, and please submit assignment number 1 separately in a file. This should be a Python file, so just mark it there. Just submit like your name underscore asg1.py. So that's it for today. I hope you can find the time to finish your 3 assignments. I don't think it's very hard. There are many examples that you can look up the internet. I think even ChatGPT is good enough for this kind of assignment, but you still need to be very careful when using them, because from my experience, or I would say from my auditing, I find that the robot is still not good enough for doing this type of research or homework. So that's it for today, and enjoy your weekend.